All right, and welcome back for lesson 5 of aqueous solutions, Beer's Law. So Beer's Law states that as the concentration of a solution goes up, its absorbance will also go up. So a solution of 0 molar, we're talking about just pure water here, will absorb 0 light. So 0 light, 0 absorbance. All the light should pass straight through this solution. And that's what we're showing here. A stream of light goes straight through the solution, and all of the light comes right out of the other side. As you start to increase the concentration of our solution, so again down here we can see we're working with a 0.05 molar solution on test tube number 2, a slightly greater concentration. We shine the same amount of light, a little bit less is going to make it through. We look at test tube number 3. We now have a 0.1 molar solution, so twice the concentration of test tube 2. And we're going to shine the same amount of light at the solution, but more of that light is going to be absorbed by the solution, and less is making it through. We move up to test tube number 4. We've again increased our concentration. We now have a concentration of 0.15. We shine the same amount of light, and even a smaller amount makes it through. More and more light is being absorbed as you increase the concentration of the solution. Test tube number 5 now, our greatest molarity, and is also going to lead to our greatest absorbance. Very little light makes it through this solution because most of it is absorbed by the solution itself. We can then use this data to build a graph. We can plot the points. We put concentration and absorbance on our axes. We plot our known data. So for instance, we might be able to say, hey, a solution of 1.5 molar has an absorbance of 0.6 absorbance. It's kind of difficult. Absorbance doesn't have units. So we just say ABS for absorbance. We do our same thing for our 0.3 molar, our 0.5 molar, our 0.6 molar. We plot those points. We apply a line of best fit, and that is going to allow us then to put an unknown concentration, find the absorbance of that unknown concentration, and we can then figure out the molarity, the concentration, even though it was unknown to us at first. So let's take a look at how we do that. We generally use a device called a spectrophotometer, and here is generally what that looks like. This is just the base unit here. You have your display up top. This is where you're going to load your sample. I'll show you that in just a second, and this is where you're going to adjust for your wavelength of light. How a spectrophotometer works is it's going to shine light through a prism. The prism is going to diffract that light into several different colors. You're then going to select a wavelength to shine through your solution. And on the other side then of the light from your solution is a detector which will pick up how much light makes it through the solution. That is what's going to be displayed over here. So here's probably a wavelength of light, 540 nanometers. Right now, it doesn't look like there's a sample in there, or if it is, it's probably a 0 molar solution because there is 0 absorbance recorded. So all the light is making it straight through on our image here. So step 1 when using a photospectrometer is to determine what the optimum wavelength is for your particular solution. Most solutions are going to have a different wavelength of light that they absorb best. So what you're going to do is you're going to put your stock solution into what's called a cuvette, which is a little square plastic piece that fits again right into the chamber here. You load the chamber, and then you're going to select different wavelengths of light. So you might start off at red light, you see that here, then move to yellow light, green light. More than likely you're going to do all the different colors of light, several different attempts. You're going to try to find, again, what optimum wavelength, what color light your solution absorbs the best. So here we might have data that looks like this. We have our wavelength. We selected, we took a look at the absorbance at several different wavelengths, 400 nanometers, 450 nanometers, 500 nanometers, 550 nanometers, and 600 nanometers. And at those different absorbances, or at those different wavelengths, we had these different absorbances. Now this will not be a linear relationship. Generally you'll have one peak. You may even have multiple peaks. When that's the case, you want to choose your highest peak. That is the wavelength of light that your solution absorbs the best. That's your optimum wavelength. For this one, it's 450 nanometers. Again, every solution is going to have a different wavelength that it absorbs light best at. Now, generally, again, we went up by 40 nanometers at a time, or 50 nanometers at a time. Usually, you're going to have smaller intervals, maybe 10, maybe even 20, and you're going to have a lot more variation, so you can really, really zero in on that peak absorbance. So, for instance, perhaps our peak absorbance is closer to 440 than 450. If we were doing this live in real life, we might break it down and look at closer wavelengths to find the exact optimum wavelength. But for this particular example, we only went by 50s, and we'll call 450 our maximum absorbance wavelength.
This is an intercom test page.
All right. So the next step is to use your salt and make your stock solution. So here we have a known solution. We'll call this one 0.5 molar. We've made our stock solution 0.5 molar. Next, you want to make dilutions of known concentration. So here is our 0.5 molar.
Testing 1, 2, 3.
And we'll make several dilutions. So we'll dilute with water. We'll call this particular dilution a 0.4 molar. We'll make another one. Add some more water. Call this one a 0.3 molar. And make a third solution, or dilution. Make this one even more watery, 0.2 molar, we'll call it. Now that we have our known solutions, we'll want to record their absorbance at our peak absorbance, which again was 450 nanometers. We're going to set that 450 nanometers. We'll keep it there, and we'll find each of our known solutions absorbance. So here's our 0.2 molar. Looks like our data suggests we're about 0.27. Here's our 0.3 concentration, our 0.4 concentration, and our stock solution, which was 0.5 molar. Again, we recorded our data here, and we were able to plot the data and apply a line of best fit. Something to point out, this one goes through the origin at 0, 0. Oftentimes you won't have a 0, 0 origin. It is common to make a 0 molar solution. Think about that. That'd just be pure distilled water. Oftentimes, though, it still has some absorbance. There are still some minerals floating around. There are some things, even in distilled water, shouldn't be, but there are. So you will oftentimes have some absorbance even at 0 molarity. So usually we do run a sample cuvette of 0 molar and count that as one of our data points, and it may not be at 0 absorbance, maybe just above that. That's fine. Have your line of best fit. Get as close as possible to that data point as well. So again, we have this data point, and the usefulness of it is it allows
Check
us...
1, 2. Intercom test page.
It allows us to find an unknown concentration. So here we have an unknown molarity, this orange solution. We know it's going to be somewhere between our known concentrations. We're not sure exactly where. We can fill a cuvette, put it into our machine, find an absorbance. This one looks like the absorbance was at 0.45. So we'll follow that out till we hit the line of best fit, follow it down, and voila, a 0.45 absorbance. Looks like it'd be roughly a 0.36 molar solution. And now all of a sudden we know the concentration of our unknown solution. Hey, you've got a homework. It's all geared towards running a Beer's Law lab. So you're starting off, question 1, you're making or describing the preparation of a 250 milliliter stock solution. Question 2, you're describing how you're going to make your 4 unknown dilutions. Don't forget your 5th dilution, or your 5th data point would be your stock solution, at 0.4 molar, not diluted at all. Part 3 then, you are given a data set here, and using this data set, you need to determine what your peak wavelength is. Step 5, you've got 3 more data points. You only need to choose one of these 3. Whichever one is your peak wavelength, you'll choose that one, and you'll plot that particular set of data, and then find the concentration of the unknown sample. There's your homework. Take a look. Good luck. We'll take a look at it tomorrow.